Hello, everyone. We are from Hillfield Strathallan College, and we will be presenting our study, investigating existing wind turbine fleets and modeling optimal geographic locations for future wind farms in Southern Ontario. In 2015, the Paris Agreement targeted reducing annual carbon emissions to under 2 tons by 2050. Producing over 7 times the global target, Canada must invest in clean energy sources in order to meet its commitments. Wind energy is the fastest growing clean energy in the country and is likely to become one of the most prevalent sources of energy. Wind energy has 3 main advantages. Canada has an abundance of wind resources, the second most in the world. Wind turbines emit extremely low waste, making it one of the most environmentally friendly sources of energy on the planet. Additionally, it is projected that by 2023, it will be significantly cheaper to produce than all other power sources.
Let us first explore the context of this study by looking at how wind energy is produced. Figure 1.2 shows a wind turbine configuration. These rotor blades capture kinetic energy from the wind and convert it into rotational motion. The rotation of the generator then produces electricity. From figure 1.3, the wind power curve shows that below the cut-in speed, the turbine will not operate. At above the cutoff speed, the turbine will be shut off due to safety reasons. Between the cut-in speed and cutoff speed, the equation indicates that the total energy output is affected by 3 main factors: air density, wind speed, and rotor sweep area. Ontario is a leading energy producer in Canada, producing 40% of all wind energy in the country. On average, the output is 8% of Ontario's annual electricity demand. As seen in figure 1.4, Ontario is projected to have an electricity deficit by early to mid 2022. As such, it's crucial that the province sources clean energy supply without increasing emissions.
We'll now briefly talk about the methods used for data collection, stats testing, and modeling. We collected data from the 3 main sources as shown. First, we collected electricity demand, output, and power plant availability data from the Ontario Independent Electricity Systems Operator. Then, we collected technical configurations and locations for wind farms using the Canadian Wind Turbine Database. Finally, we collected weather data from the Copernicus Climate Change Service. As seen in figure 2.1, we created a correlation heat map for the process data to identify any multicollinearity. It was noted that no multicollinearity exists. Next, we put the data into a k-nearest neighbors algorithm to determine the approximate size of the outlier set and found that it represented about 5% of our total data. This data was kept to make our model more robust and less sensitive to large changes. On the right, we can see figure 2.2, and the region bounded in red is considered Southern Ontario. This region will be the main focus of our study. We processed our data by removing any missing entries and used standardization to create a normal distribution with mean 0 and standard deviation of 1. For our model, we chose a neural network with 3 hidden layers and 4 neurons in each layer. Our goal is to predict daily energy generation using 6 different input factors: temperature, wind speed, air pressure, relative humidity, precipitation, and available capacity, which is the rated capacity minus any capacity lost due to maintenance or downtime. To model the energy generation, a list of locations were generated in Southern Ontario. For each of these locations, we collected historical weather data and loaded them into the neural network to get energy generation predictions. Finally, to evaluate our model, we have used k-fold cross-validation and various different train test sets.
Now on to our results. First, we investigated the geographic distribution as well as fleet composition. In figure 3.1, we plotted the latitude and longitude of all existing wind turbines across Ontario. 86% of Ontario's total wind turbines are in Southern Ontario. In table 3.1, we listed the age and manufacturers of all active wind turbines in Southern Ontario. It can be observed that 72% are from turbines 10 years old or younger. Additionally, Siemens was the leading manufacturer, accounting for over 40% of installed capacity. Second, we considered technical enhancements in the turbine fleet. Shown here are graphs of unit capacity, hub height, and rotor diameter over the years. It can be observed in figure 3.2 that the turbine capacity has quintupled from 2001 to 2019. Additionally, both rotor diameter and hub height have increased steadily and significantly over the same period, as shown in figure 3.3 and 3.4. Third, we analyzed the performance of the wind fleet by comparing hourly average wind output to electricity demand. As depicted in figure 3.5, electricity demand was highest in the summer and winter, while being lowest in the spring and fall. Additionally, its electricity output for wind energy was lowest in summer and the highest in winter. To further understand this trend in output, we analyzed the wind speed data of the four corners of our area of focus as indicated in figure 3.7. The average wind speed for these locations can be seen in figure 3.6. It was observed that the wind output and monthly wind speed followed a similar trend. Then, to identify the Ontario wind fleet strengths and areas of improvement, we thoroughly examined a self-pull Southern Ontario wind farm, Cedar Point. It was commissioned in 2015 near Sarnia Airport with a total rated capacity of 100 megawatts. Figure 3.8 plotted the wind speed data for every hour of the 2020 year. It can be noted that wind output for this wind farm varied dramatically over the hours, days, and months, from as low as 0 megawatts to as high as 99 megawatts. Additionally, there was a far greater concentration of data points in the bottom quarter of the scatter chart, particularly during summer months. Figure 3.9 shows the daily range of wind speeds in 2020 at the nearest Glover station. It appeared that wind speed changed dramatically over the hours, days, and months, none too dissimilar to Cedar Point's wind output. Finally, figure 3.10 is the pie chart for the actual hourly wind output at Cedar Point in 2020. We observed that around 75% of the time, output was at half of its rated capacity. Of this, a quarter of the time had no output at all. Using the same method, we researched an additional 6 wind farms. The technical data and results of the 7 investigated sample farms are listed here on table 3.2. All farms are 5 to 11 years old, and in 2020, availability for all sample farms was over 98%, but capacity was only in the range of 0.24 to 0.33.
Here are the 7 top-ranked locations by annual energy generation for the neural network. All of these locations have free land and are not located in the vicinity of any newly commissioned wind farms. As seen in figure 311, the 7 locations are plotted, and in descending order of annual energy generation, they are Tobermory, Con, Kincardine, Port Colborne, Fairmount, Long Point, and Leamington. For neural network evaluation, we used tenfold cross-validation and achieved excellent results of a 5.52% mean absolute percentage error. Our model also captures almost all of the variance displayed in wind energy generation with a R-squared value of 0.983.
Let's now move on to the discussion. Figure 4.1 represents the age composition of Southern Ontario wind turbine fleet. It can be observed that in 10 years, 28% of the current wind turbine will be due to retirement due to their age, assuming a life expectancy of 20 years. Figure 4.2 represents the relationship between the maximum rated unit capacity and the rotor diameter over the past 20 years. The 5-period moving average of wind turbine hub height and the rotor diameter shows that a gain capacity tapered after 100 meters, suggesting that a further expansion in rated unit capacity from those factors will be very limited.
Performance of Ontario wind farms. The yearly capacity factor is the ratio between actual and rated energy output and is used for comparing wind farms. In Ontario, the provincial average was 0.28 in 2020. In the US, the fleet-wide average was 0.35. By comparison, Ontario's wind capacity factor is much lower and has much room for improvement. As we cannot control wind variability, wind power is often misaligned with electrical demand. The ratio between the wind power and electrical demand is lowest in the summer at 4.4% in July and highest in late winter with 12.6% in March. This is yet to be a major concern, as wind power only satisfies a moderate 4 to 13% of monthly electrical demand. However, as wind power grows into a larger player, this fluctuation could cause substantial surpluses or shortages to the power grid. Thus, as wind power is further developed, energy storage systems need to be planned simultaneously.
In conclusion, the Southern Ontario fleet is large, young, and reliable. It currently has an installed capacity of over 5,000 megawatts. Over 99% of the fleet is also 15 years old or younger. For all sample wind farms investigated, availability in 2020 was over 98.7%. However, the capacity factors of Ontario's wind fleet were on the lower end of the industry standard at around 0.28. Regardless, Ontario is the leader in wind power in Canada. Depending on the season, wind power contributes from 4 to 13% of monthly electrical demand, with an annual average of 8%. With Ontario promoting wind energy as one of the main sources of clean electrical power, this number will only continue to grow in the coming years. To address this trend, further data analysis and modeling has been conducted to recommend 7 geographic locations for potential future wind farm development in southern Ontario. Additionally, as the Ontario wind turbine fleet ages, turbines will be due for decommissioning or repowering. Further research should be conducted to properly process decommissioned and demolished turbines. Finally, the installed capacity factor of Ontario's wind fleet was noted to be quite low compared to the industry as a whole. Research is needed to identify the root cause of this weak performance and to determine proper remedies. Thank you.